Here is Unit 5, Geology, Lesson number 5, Earthquakes. So we've learned that the crust is always moving, and sometimes when it moves, it kind of slips in a way that generates a bunch of energy that radiates out through the rock. So a good definition we can use for earthquake is just vibration of crust produced by energy released from slippage. So a couple of terms that we need to talk about in relation to earthquakes are the focus or hypocenter. This is the underground origin of an earthquake where the rocks actually slipped against each other and where the actual place where the earthquake occurred is, and that's underground. And then these earthquakes can be shallow, intermediate, or deep. It just depends on how close to the surface they are. Shallow focus earthquakes are the most damaging because the further an earthquake wave has to travel to get to the surface where all of our stuff is, the more energy it loses as it travels through all that rock. So the closer the focus is to the surface, the more damaging it's going to be to our stuff on the surface because it doesn't lose as much energy as it's traveling. And then the epicenter of an earthquake is the term you've probably heard of more often. And that's just the point directly above the focus on the surface of the earth where we can say the earthquake originated from. So there are two major areas on Earth where earthquakes like to occur. One of them is subduction zones. So remember, subduction zones happen at convergent plate boundaries where two plates are moving together. One is going to sink beneath the other one in the process called subduction. So that's why it's called a subduction zone earthquake. As that happens, the plates grind against each other, and that can create the energy that leads to earthquakes. So a lot of these happen. Usually they're going to be deep focus. So you can see here, this is the outline of the Pacific plate of the lithosphere. And right here, where all of these red means deep focus, all of these red earthquakes, this is where an active subduction zone is. So this part of the Pacific plate is actively sinking beneath these plates over here. The same is true right here. This is the Nazca plate, and this is the South American plate. The Nazca plate is moving in this direction and subducting beneath the South American plate. So we have the deep focus earthquakes happening here and happening here at these two majorly active subduction zones on Earth. The other places where earthquakes like to occur are at fault lines. So fault lines are just cracks in the lithosphere. If a fault line is really, really big, traveling through a whole entire plate, it can be called a transform plate boundary. So these fault line earthquakes typically are more shallow or intermediate focus because the faults don't usually run all the way through the plate like they do at transform plate boundaries. This is what causes the earthquakes that we get in Helena. So here is a picture of the Helena Valley. This yellow line is showing a fault. If you can look closely here, this road traveling right here is Green Meadow. So if you went all the way this way on Green Meadow, you get to Capitol High School way down here. Here's a map of the Helena Valley just showing these red dotted lines are just some examples of where faults exist. You can see here's Canyon Ferry Lake, here's the town of Helena. And so there's lots of different faults that run all through the Helena Valley, and when those faults move a little bit, they can create earthquakes. There are three major types of faults. The first we're going to talk about is the normal fault. Normal faults occur when there is tensional stress. So when you have stress pulling on, these are called fault blocks, the two pieces of lithosphere that have the crack running in between them. When you have stress that pulls the two fault blocks apart, what's called the hanging wall will slip down. And this is a little animation kind of showing that as that hanging wall slips down, that's what generates the energy that creates the earthquake. So the second kind of fault is a reverse fault, and this is pretty much the opposite of a normal fault. So this is compressional stress, when you've got your two fault blocks being squeezed together, being compressed together. This time the hanging wall gets pushed upwards, so you can watch in the animation here, our hanging wall gets pushed upwards, and that's what releases the energy that creates the earthquake. So the last type of fault we're going to talk about is a strike-slip fault. Strike-slip fault results from shear stress. So we don't have a hanging wall and footwall being pushed against each other. Now we have two pieces of crust that are just sliding past each other. If these are really, really big, these can be transform plate boundaries. Transform plate boundaries are just huge strike-slip faults. So you can watch in the animation here, you've got your two fault blocks. As the energy is released here, the earthquake happens as the two blocks slide past each other in a shear motion. So the energy released by earthquakes travels in really specific wave patterns. The first we're going to talk about is the P wave. P stands for primary. These are the fastest type of earthquake waves, so they'll reach an earthquake recording station first. They move in a compressional or push-pull type of motion. So if you watch on this GIF, you can watch, this is how the wave moves. Just back and forth. Imagine the slinky is the material of the ground and the waves just moving back and forth, push and pull, compressional motion. P waves can also travel through solids and liquids, so they can travel through solid rock, they can travel through the liquid outer core, they can travel through water. This is not true for all types of earthquake waves. Next type of earthquake wave is called the S wave. S stands for secondary, so these are the second fastest type of earthquake wave. They'll reach a recording station after P waves. They move in a shear or side-to-side motion. So if you watch, when they wiggle the slinky back and forth, that's a shear motion. It's side to side. It's kind of like a snake snaking along the ground. So that is how the S wave moves. These can travel through solids only. They cannot travel through liquids. And so this is one way that we learned that the outer core of the Earth is liquid, because S waves can't travel through liquid. And so if you have an earthquake happen here on the planet, you don't feel any of the S waves on the opposite side of the planet, and that's because they can't travel through this liquid outer core, so that it creates a phenomenon known as the S wave shadow zone. So this area right here is the S wave shadow zone, because the S waves can't travel through this liquid to pop out on the other side of the Earth. The last type of earthquake wave we're going to talk about is a surface wave. Now there's a few different kinds of surface waves, but we're just going to lump them all together and call them surface waves. These are the slowest waves, so they'll get to an earthquake recording station after S waves. These are the most destructive kind of waves because of the way that they travel through the Earth. So the P waves traveled back and forth, the S waves traveled side to side, so that was just kind of shaking, and now the surface waves come along and they travel up and down. So can you imagine in gym class, if you've ever had to do that workout where you take the ropes and smack them against the ground? That is kind of the motion that surface waves have as they move through the Earth. So they can really mess up human structures, like here we have roads and power poles that are on the surface. There are two different scales that are commonly used to measure earthquake intensity. The first is called the moment magnitude scale. This is what replaced the Richter scale. So the moment magnitude scale is based on how much energy is released by the actual earthquake. It's on a scale of 1 to 10. So if you ever hear, oh, we had a magnitude 4.5 earthquake happen in the Helena area, this is what they're talking about. It's this moment magnitude scale. And every step up on the scale of 1 to 10 is 10 times more powerful. So you can see here, this little dot is a magnitude 5.8 earthquake, like the size of the sphere is representing how much energy was released. The 5.8 is this little guy here. Here's a 7. And so you can see just how big the jump is between a magnitude 7 earthquake and a magnitude 9 earthquake. It's 10 times more powerful each step you go up on the scale. The other scale that's used a little bit less commonly is called the modified Mercalli scale. And this scale is based on how much damage is done by the earthquake. It's on a scale of 1 to 12 in Roman numerals. So here's the modified Mercalli scale. A 1, earthquake is barely felt. It doesn't do any kind of damage. A 12 is like a total cataclysm. Everything is destroyed. People are dead. The landscape is changed. So those are the two most common scales that are used to measure earthquake intensity. So just a little bit more here about how we measure earthquakes. A seismologist is the earthquake scientist. So here's some seismologists out in the field, and they're using a tool called a seismograph. Here's a picture of a seismograph. It's a tool that has like a drum of paper and a needle that wiggles back and forth as earthquake waves travel through it. So the seismograph creates a paper readout that's called a seismogram, and these seismologists can analyze a seismogram to tell what the magnitude of the earthquake is and also how far away the earthquake was from wherever the seismograph was sitting. So again, P waves are the fastest, so they'll arrive first on a seismogram, followed by S waves next, and then surface waves last because they're the slowest. The way that we locate where earthquake epicenters is through a process called triangulation. Triangulation sounds like triangle, and a triangle has 3 sides. So through the process of triangulation, we can use data from 3 different earthquake recording stations to figure out where the epicenter was. And the way that seismologists do this is they look at the difference between the arrival time of the first P wave and the first S wave on a seismogram. And the longer the distance is, that means the further away the earthquake was. So here's an example. P and S waves are really close together from station A. That means the distance is small. For station B, it was a little bit longer, so the circle is a little bit bigger. Station C, it was even longer yet, so the circle is even bigger. So what they do is they have a standard chart that means like, oh, if the distance between the P and the S wave was this far apart, that means this is how far away the epicenter was. So they've done that for these 3 recording stations here in Salt Lake City, Savannah, Georgia, and Houston, Texas. And so they calculated using that chart that the earthquake was 1,800 kilometers away from Salt Lake City. So they drew a circle with a radius of 1,800 kilometers around Salt Lake, meaning that the epicenter of that earthquake is somewhere along this circle. They did the same calculation for Savannah and got 1,300 kilometers, and for Houston they got 800 kilometers. So they drew a circle around Savannah at 1,300 kilometers, a circle around Houston at 800 kilometers, and this spot here, exactly where all three of these circles intersect, that is where the earthquake epicenter is located. So moving on to some of the hazards that are associated with earthquakes. Probably the most devastating one is the tsunami, and a tsunami is a giant ocean wave that's caused by an earthquake. So you can watch in this animation, here is the ocean crust, there is the release of energy, it pushes the water upward, and then giant waves radiate outward from the epicenter of that earthquake. So here in this animation, this is showing how ocean waves can travel, tsunamis can travel across an entire ocean. From one earthquake that was generated right here, a tsunami traveled all the way across the Indian Ocean to the east coast of Africa. And so here is a little video showing kind of what a tsunami can look like. This is from a tsunami that happened in Japan in 2011. You can see that the water just destroys everything in its path. And one of the dangerous things about a tsunami is that before a tsunami is going to hit, the water recedes really far away from the beach, farther than it usually goes. And so sometimes people like these people went out because they're like, oh cool, look, a bunch of beach that we didn't see before. So they went out further than they should have, and then the tsunami rushed in. This was a tsunami that happened in 2004. It's this same tsunami that is shown in this animation here. And this tsunami killed almost 250,000 people because of how enormous the wave was and the destruction that it caused. Another type of earthquake hazard is called liquefaction. It's not liquefaction, it's liquefaction. And liquefaction happens when you have wet soil that as earthquake waves travel through it, it kind of turns that soil into a liquid rather than a solid. Here are some videos. You can see that happening as the ground moves with the earthquake. You can see little bits of water jetting upward out of the ground that just moments before was completely solid ground. Here's another one. You can actually see the motion of the ground here, and you can see the water being forced out of the soil. And this is so dangerous because we can watch this animation here. When you have sediment that is saturated by water and it gets shaken by an earthquake, you can see that as the liquefaction occurs, the ground that was solid before becomes much less stable, and structures that are built on that ground can tip over and be destroyed. So the final couple of hazards that are associated with earthquakes are unstable buildings and fires. So here is a little video of an earthquake that happened in Nepal. And so you can see that as the earthquake happens, this building was not built to withstand earthquakes, and so it just crumbles apart and big pieces of debris fall, and those can crush people. This picture here it's a colorized picture from 1906. There was a major earthquake that struck San Francisco, and that earthquake shifted the ground so much that a lot of the gas pipelines underground were broken, and the gas leaked out, and any kind of spark can cause a huge fire. And so a lot of people died in the fires in San Francisco in 1906 that were caused by an earthquake.